So these notes are for Unit 1, Transformations, and it is the topic about non-trig parent functions. And it's just a quick overview of all the parent functions that we will be working with in the first semester of AP Pre-Calculus. So for our first function, we have f of x equals x. For some reason, the picture did not get put on here, so go ahead and draw it in yourself. And we have a linear function with a positive slope, or a slope of 1, so therefore it is increasing through the origin here. With each of these, you're going to see the parent function, a table of values that we use for transformation tables, and then you'll have a graphical representation of that function. So with this one, our three key points are going to be at -1, -1, 0, 0, and -1, -1. And then below that, you will see a list of attributes for each parent function. The first attribute will be whether it's even, odd, or neither. So with this one, we can see that we have that rotational symmetry. When I take this portion of the graph and I rotate at 180 degrees around the origin, I can see that it's going to overlap itself. Therefore, f of x equals x is an odd function. You can use the degree. It is a degree of 1, therefore it could be odd, but if you have certain transformations applied to an odd function, it's not always going to stay odd. It has to have that rotational symmetry about the origin. The domain and range are both all reals. You can say that, or you can use I call it the three-dimensional R, or you could use the interval notation, which is -infinity to infinity. We want to be efficient though, so the quickest way to write this is using this notation. The next function is going to be x squared. This is going on forever in both directions. The key points are going to be -1, 1, 0, 0, and then 1, +1. Again, we use the key points when we create our transformation tables. This one is an even function because if we take the right side of the graph and we close it like a book, it will exactly overlap the left side of the graph. Therefore, the function is even because it has that reflective symmetry. Again, the domain is going to be all reals because it's going on in both directions forever. And the range is going to be from 0 up to +infinity. The next one is going to be f of x equals x cubed. This one is also going on forever. Key points are going to be -1, -1, 0, and then 1, 1. Similar to the linear function, but this one's going to have that curvature, or we haven't really talked about this yet, but we can see that it's going to change its concavity at the origin. All right, so we still have the same key points, but the curvature of this function is way different than f of x equals x. This is an odd function because if we were to rotate this 180 degrees about the origin, the function would overlap itself. So as we come around here, we can see that this curve will be the same in quadrant 3 as it is in quadrant 1. And the domain and range are all real numbers. Next on the list is going to be the absolute value function. It is going on in both directions. And just like the quadratic function, the key points are -1, 1, 0, 0, 1, 1. Again, same three key points, but very different attributes. This is an even function because it has that reflective symmetry. Whatever is on the right side of the y-axis is going to overlap on the left side of the y-axis if we close it like a book. Domain is all reals, and then also like the quadratic function, the range is from 0 to infinity. Now, we are going to be talking a lot about piecewise functions in this course, and we'll have a full day for this later, but I want to go ahead and introduce it to you now if you haven't seen it. So we have f of x, which is equal to the absolute value of x. We are able to rewrite this as multiple functions, but it's going to be pieces of multiple functions. If we look at the left side of this absolute value, we can see that we have a linear function, but it's decreasing in value, or the slope is negative. Particularly for this one, the slope is -1, so we will have -x. And then on the right side of the y-axis, we can see that it is another linear function, but instead of the slope being -1, it is +1. We are able to write absolute values like this. So the absolute value of x is equal to plus or minus x, all right? And this is where I'm getting that piecewise from. Depending on what's inside of the absolute value, this will change, and we will see that later. Now, this is not true for all reals. The slope is not -1 for every single point on this function. It is only true when x is less than 0. The same can be said for this one. The slope is only positive when x is greater than 0. This piecewise has to represent every single real number. And right now we're missing the 0. For this particular absolute value function, this could go either way. It could go with the negative x, or it could go with the x. I'm just going to choose the top one. It doesn't matter which one you choose, but it cannot be both. It has to be one or the other. And then for specific situations, it will go with one or the other. Say that the endpoint is non-inclusive, but for this one, it's inclusive, so therefore we can pick either side. This next function is going to be your exponential function. Actually, we'll look at both of these. Both of these are our exponential functions. Exponential functions have a new attribute that we haven't seen yet with our previous parent functions. They all have horizontal asymptotes. So we'll have a HA, or horizontal asymptote, at y equals 0. And then same goes for this one. For e to the x, it will have a horizontal asymptote at y equals 0. The reason being is there is no value that we can plug in for x that will create an output that is negative, right? Because if that exponent is negative, say that we have 2 to the negative 1, that's not going to create a negative output. It simply gives us the reciprocal, and then we're going to have a small number. So the smaller that negative number is, the smaller the smaller the decimal value will be for that output. And I want you to notice for these table of values for both of them, when we are using exponential functions, the special key points are going to be -1, 0, and +1. So very similar to our other functions. So -1, 0, and +1. If you take a look at this, because we just did this example, 2 to the -1 is equal to 1/2. Therefore, the output is going to be 1/2. So if b is equal to 2, that means the b is going to be in the denominator. Same thing here. The base is equal to e. Therefore, the e is in the denominator. And then anything to the power of 0 will be equal to 1. So it's going to be the same for both of these. So we see that in the table of values. And then anything to the power of 1 is going to be equal to itself. E. And then just keep in mind, e is not a variable. It is a constant. All right. We'll talk more about, it's called Euler's number, but it has a value of 2.71 and it goes on. Okay. So that is a constant. It is not a variable. Both of these are they are neither odd nor even because they don't have that rotational symmetry about the origin, nor do they have that reflective symmetry. All right, so functions don't have to be even or odd. Most of them are going to be neither based on their attributes from the parent function, or if you apply certain transformations to parent functions that are usually even or odd. All right, now we're going to look at the inverses of the exponential functions. So let's see if I can connect these. So log base 2 of x is actually the inverse of 2 raised to the power of x. And then natural log of x is going to be the inverse of e to the x. And then we're going to talk, you did inverses. It was one of the last things you did in Algebra 2. We're going to talk about those later. So for this one, because log base 2 of x is the inverse of 2 raised to the x and y values are going to change. All right, so now what we saw as the outputs, those are going to be the inputs for the log. Same thing over here. Just remember that natural log of x is equal to log base e of x. The same thing is going to happen here. The inputs and the outputs change. Now notice that in the previous ones, we had a horizontal asymptote. That is when they are in the x column, all right? Because our horizontal asymptotes are going to be equations that equal y, that means they will be at 0. And since we are switching x and y, now our y values are going to show the vertical asymptote. Sorry, not the y values will show the vertical asymptote. The vertical asymptote is vertical, so that means we're going to have to use the x's to show where those are located. So both of these have vertical asymptotes. Again, their inverses are neither odd nor even, therefore the inverses will neither be odd or even as well. Domains are non-inclusive, 0 to infinity, but the ranges are all reals because they go forever in both directions. All right, the next function is going to be the square root of x. This one does start at the origin 0, 0, and then it is going to go on forever in the positive direction for x values and y values. Our special points are going to be 0, 1, and 2. And then we have 0, 1, and 4 So let me fix those points real quick. So 0, and then it's hard to see on here. This should be 1, and then 2, 3, 4. There we go. Okay, hopefully it's better on your notes though. And then just keep in mind, we're going to talk more about this, but you can rewrite this as x to the power of 1/2. So whatever that root is, it's going to be the fraction for the exponent. Again, neither odd nor even. It doesn't have that reflective symmetry or that rotational symmetry about the origin. And the domain is from 0 to infinity for both domain and range. So you could also say x is greater than or equal to 0, or y is greater than or equal to 0 for that inequality notation. All right, coming to our rationals, these also go on forever in all these directions. Rationals are going to have two asymptotes. We're going to have a vertical asymptote and a horizontal asymptote. So the vertical asymptote is going to be at x equals 0. Horizontal asymptote will be at y equals 0. And we can see that inside of the table. We only have two key points on the actual curve. That's going to be at -1, -1, and then 1, 1. This is an odd function because if we look at this curve here, if we were to rotate it about this way, this arrow would overlap this arrow, this one would overlap this arrow. Therefore, we have that rotational symmetry, so it is an odd function. And you could say that the domain is -infinity to 0, non-inclusive, and then union 0 to infinity, but it's more efficient to write it like this. We include all real numbers except for when x is equal to 0, so we can just say x does not equal 0. And we can do the same thing for the domain, or I'm sorry, for the range. If you see this, I'll bring this back. Actually, I can just use, I can't use that anymore. So -infinity to 0, union, 0 to infinity. This u, it means union. And that just means the two intervals that do not overlap. So that's all that means. We'll be using union a lot. I can't remember if y'all used it last year or the previous year, but we're going to be seeing union a lot. All right, for this one we have 1 over x squared. So now this one will also have a vertical asymptote and a horizontal asymptote. And they will be the same as the previous one. The vertical asymptote is at x equals 0. Horizontal asymptote is at y equals 0. This one is an even function. Because it has that reflective symmetry about the y-axis, we're able to close it like a book, and it will overlap itself. The domain is all real numbers except for when x equals 0, so x cannot equal 0. And then the range is different. This is going to be all values above 0 because of that x squared. So all values will be positive. Just keep in mind that we can rewrite this as x to the power of -1. This one can be written as x to the power of -2. All right, from here we have the cubed root of x. This one can be written as x to the power of 1/3. And then the key points for this one are going to be -1, -1, 0, and 1, 1. This one is an odd function because we have that rotational symmetry. And then the domain and range are all real numbers. So keep in mind that this is the inverse of x cubed. All right, and the last function that we're going to look at, which is probably the only new function. Well, it is. You've seen all the other functions. This is, well, actually, make sure that you fill in these here. Okay, this is called the greatest integer function. Greatest integer function. Or the nickname is step function for obvious reasons. All right, so this one is neither odd nor even though it kind of looks like y equals x, but the issue is if we were to take this particular section and we rotated it 180 degrees, it would end up looking like this. Okay, so it's close, but now these are not overlapping. the non-inclusive and the inclusive endpoints for each of those bars is not overlapping. Therefore, it is neither odd nor even. But the domain is all reals because even though this is a hole here, there is an output value for that particular x value, and that happens for every single part of this. So therefore, the domain is all reals. The range is going to be, it's just integers, so it's all integers, all integers. Or you can say that where k is equal to any integer because there's no decimal values, or k is an integer, and you can use the z for that. So just like all reals, it's a three-dimensional z. I think it's German. I forget. I'll talk about more of that in class, but it's from the German, or it's from German. And how we evaluate this is that, say I want to evaluate, let's say f of 2.8. I'm going to plug in 2.8 into this step function. The notation is brackets. So I have 2.8. And if I look at this, so I have, this is from 1 to 2. Sorry, that's from 0 to 1. This is from 1 to 2. And then this is from 2 to 3. 2.8 is about right here, which means if I evaluate 2.8 on this function, it's just going to be 2. So we are using the integer that is part of that decimal. All right, and that's the first topic. That's just reviewing parent functions. And the next topic will be verifying even or odd functions.